The James Webb Space Telescope, JWST, often referred to as the successor to the Hubble Space Telescope, has revolutionized our understanding of the cosmos since its launch in December 2021. With its unprecedented infrared capabilities, the JWST has peered deeper into the universe than ever before, uncovering secrets that were once thought to be beyond our reach. Among its many groundbreaking discoveries, the telescope has provided new insights into one of the most enigmatic and fascinating objects in the universe: black holes. Black holes have long captivated the imagination of scientists and the public alike. These cosmic phenomena, where gravity is so intense that not even light can escape, have been the subject of countless studies, theories, and science fiction stories. Despite their popularity, much about black holes remains shrouded in mystery. How do they form? What happens inside them? And what role do they play in the evolution of galaxies? The JWST has begun to answer these questions, offering a glimpse into the inner workings of black holes and shedding light on their profound influence on the universe. This article delves into the latest discoveries made by the JWST regarding black holes, exploring the telescope's capabilities, the nature of black holes, and the implications of these findings for our understanding of the cosmos. The James Webb Space Telescope, a new era in astronomy. Before diving into the specifics of black hole research, it's essential to understand the capabilities of the JWST and why it represents such a significant leap forward in astronomy. The JWST is a joint project by NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. It is equipped with a 6.5-meter gold-coated beryllium mirror, which is nearly 3 times the size of Hubble's mirror, allowing it to collect more light and observe fainter objects. One of the most critical features of the JWST is its ability to observe in the infrared spectrum. Unlike visible light, infrared light can penetrate cosmic dust clouds, revealing objects and phenomena that are otherwise hidden. This capability is particularly valuable for studying black holes, which are often surrounded by dense clouds of gas and dust. The JWST is also equipped with a suite of advanced instruments, including the near-infrared camera, NIRCam, the near-infrared spectrograph, NIRSpec, the mid-infrared instrument, MIRI, and the fine guidance sensor/near-infrared imager and slitless spectrograph, FGS/NIRIS. These instruments allow the telescope to capture high-resolution images, analyze the chemical composition of distant objects, and study the formation of stars and galaxies. Understanding black holes, the basics. Black holes are regions of spacetime where gravity is so strong that nothing, not even light, can escape. They are formed when massive stars collapse under their own gravity at the end of their life cycles. The boundary surrounding a black hole, beyond which nothing can escape, is known as the event horizon. There are several types of black holes, including stellar mass black holes, supermassive black holes, and intermediate mass black holes. Stellar mass black holes, which are typically a few times more massive than the Sun, are formed from the collapse of massive stars. Supermassive black holes, which can be millions or even billions of times more massive than the Sun, are found at the centers of galaxies, including our own Milky Way. Intermediate mass black holes are a less well-understood class, with masses between stellar mass and supermassive black holes. Black holes are invisible by nature, but their presence can be inferred through their effects on surrounding matter. For example, when a black hole pulls in gas and dust from its surroundings, the material forms an accretion disk around the black hole. As the material spirals inward, it heats up and emits radiation, including X-rays, which can be detected by telescopes. The JWST's observations of black holes. The JWST has provided new insights into black holes by observing their effects on their surroundings and by studying the light emitted from the regions near their event horizons. Here are some of the key discoveries made by the JWST. The structure of accretion disks. The JWST has captured detailed images of the accretion disks surrounding black holes, revealing the complex dynamics of the gas and dust as it spirals inward. These observations have provided new information about the temperature, density, and composition of the material in the disks, as well as the processes that drive the accretion. The role of magnetic fields. The JWST has also observed the role of magnetic fields in the behavior of black holes. Magnetic fields can influence the flow of material in the accretion disk and can even launch jets of particles that travel at nearly the speed of light. The JWST's observations have shown that magnetic fields play a crucial role in shaping the environment around black holes and in the emission of radiation. The growth of supermassive black holes. One of the most significant questions in astrophysics is how supermassive black holes grow to such enormous sizes. The JWST has observed distant galaxies and their central black holes, providing new insights into the processes that drive their growth. These observations suggest that supermassive black holes grow primarily through the accretion of gas and dust, as well as through mergers with other black holes. The influence of black holes on galaxy evolution. The JWST has also studied the impact of black holes on the evolution of galaxies. Supermassive black holes are thought to play a crucial role in regulating the growth of galaxies by heating and expelling gas, which can prevent the formation of new stars. The JWST's observations have provided new evidence for this feedback process, showing how black holes can shape the structure and evolution of galaxies over cosmic time. The search for intermediate mass black holes. The JWST has also contributed to the search for intermediate mass black holes, which are thought to be the missing link between stellar mass and supermassive black holes. By observing the motion of stars and gas in distant galaxies, the JWST has identified several candidates for intermediate mass black holes, providing new clues about their formation and evolution. One of the most exciting areas of research enabled by the JWST is the study of the regions near the event horizons of black holes. The event horizon is the point of no return, beyond which the gravitational pull of the black hole is so strong that nothing can escape. However, the region just outside the event horizon, known as the innermost stable circular orbit, ISCO, is where much of the interesting physics occurs. The JWST has observed the ISCO around several black holes, providing new insights into the behavior of matter in this extreme environment. For example, the telescope has detected the effects of relativistic effects, such as time dilation and gravitational redshift, which occur as matter approaches the event horizon. These observations have confirmed predictions made by Einstein's theory of general relativity and have provided new tests of the theory in the strong gravity regime. The JWST has also observed the phenomenon of black hole shadows, which are dark regions surrounded by bright rings of light. These shadows are caused by the bending of light around the black hole, and they provide a direct way to measure the size and shape of the event horizon. The JWST's observations of black hole shadows have provided new information about the spin and mass of black holes, as well as the geometry of spacetime near the event horizon. The role of black holes in the early universe. The JWST has also provided new insights into the role of black holes in the early universe. By observing distant galaxies and quasars, the telescope has revealed that supermassive black holes were already present in the universe just a few 100 million years after the Big Bang. This raises the question of how these black holes could have grown so quickly in such a short amount of time. One possible explanation is that the first black holes formed from the collapse of massive clouds of gas, rather than from the death of massive stars. These direct collapse black holes could have grown rapidly by accreting gas from their surroundings, eventually becoming the supermassive black holes we observe today. The JWST's observations of distant quasars have provided new evidence for this scenario, showing that some of the earliest black holes in the universe were already extremely massive. The JWST has also studied the impact of black holes on the reionization of the universe. After the Big Bang, the universe was filled with neutral hydrogen, which absorbed light and made the universe opaque. However, as the first stars and galaxies formed, their radiation ionized the hydrogen, making the universe transparent. Black holes are thought to have played a crucial role in this process, as the radiation from quasars and active galactic nuclei, AGN, could have contributed to the reionization of the universe. The JWST's observations of distant quasars have provided new insights into this process, showing that black holes were indeed active in the early universe and could have played a significant role in its evolution. The future of black hole research with the JWST. The JWST is still in the early stages of its mission, and much more is expected to be discovered about black holes in the coming years. The telescope's ability to observe in the infrared spectrum, combined with its high resolution and sensitivity, makes it an ideal tool for studying black holes and their effects on the universe. One of the key areas of future research will be the study of black hole mergers. When two black holes merge, they produce gravitational waves, which are ripples in spacetime that can be detected by observatories such as LIGO and Virgo. The JWST can observe the electromagnetic counterparts of these mergers, providing new insights into the physics of black hole collisions and the nature of gravity. The JWST will also continue to study the role of black holes in galaxy evolution, particularly in the early universe. By observing distant galaxies and quasars, the telescope will provide new information about how black holes grow and how they influence the formation and evolution of galaxies. Finally, the JWST will contribute to the search for new types of black holes, such as primordial black holes, which are thought to have formed in the early universe, and intermediate mass black holes, which are still poorly understood. These discoveries will provide new insights into the nature of black holes and their role in the cosmos. Conclusion. The James Webb Space Telescope has opened a new window into the universe, revealing the secrets of black holes in unprecedented detail. From the structure of accretion disks to the role of black holes in galaxy evolution, the JWST has provided new insights into some of the most fundamental questions in astrophysics. As the telescope continues its mission, it is expected to uncover even more about these enigmatic objects, shedding light on the nature of gravity, the evolution of the universe, and the ultimate fate of matter in the cosmos. The discoveries made by the JWST are not only advancing our understanding of black holes but are also challenging our perceptions of the universe. As we continue to explore the cosmos with this remarkable telescope, we are reminded of the vastness and complexity of the universe and the endless possibilities for discovery that lie ahead.